A great analyst, being a great data scientist who can apply these to different situations. Hello everybody. In this video series, we're going to be talking about logistic regression. Logistic regression is a machine learning model that determines or predicts binary outcomes. So it's one of two things. Some examples are if you're trying to detect fraud for financial transactions, or in the medical world, it would be determining if a patient has a particular disease. So it would determine the presence or absence of disease. It has far-reaching applications. It's an important fundamental subject in machine learning. And so this video series is going to unpack all of it and hopefully let you walk away with a full fingertip feel for using logistic regression and being a great analyst, being a great data scientist who can apply these to different situations. So how we're going to approach this is, one, we're going to work the 6 essential steps. We're going to demystify the mechanics of the coding life cycle. So we're going to go through all the different steps that go into it. Just to get a high-level overview, we're not going to understand everything, but we are going to watch it work. And then, once that's out of the way, we're going to unpack the theory and develop deeper understanding. We're going to unpack the models, the mathematical models, that's the sigmoid function and the linear combination, also called the decision boundary. Do not be intimidated. I'm sure it's understandable once you unpack it. And then we're going to get into more of the code and learning how to split the data, encode categorical variables, train, test, split, feature scaling, that sort of stuff. And these are transferable to other machine learning projects too, so don't feel like you're getting hyper-focused here. It's all going to pay off, I promise you that. So without further ado, let's get into the coding example. In this video, we're going through the 8 essential steps with logistic regression using the Pima Indians Diabetes dataset. This was collected by the National Institute of Diabetes and Digestive and Kidney Diseases. This dataset was created as part of a study to investigate the factors influencing the prevalence of diabetes among the Pima Indian population, which is known to have a high incidence of diabetes, unfortunately. Data was collected from females of at least 21 years of age living near Phoenix, Arizona. The aim was to predict the onset of diabetes based on diagnostic measurements. So the predictor variables are the number of pregnancies, plasma glucose concentration, diastolic blood pressure, skin fold thickness, 2-hour serum insulin, body mass index, a pedigree function. This is some sort of an index based on your family heritage to indicate whether or not you have a likelihood of developing diabetes. And then finally, we have the target variable. 1, this patient is known to have diabetes, or 2, they are not. So this is an important data set. It's used to develop predictive models like what we're doing here. And for machine learning, since it's so tidy, it's so well structured, it is useful to benchmark different machine learning models. So that said, let's get into these essential steps. I've listed them all here. I've sort of pre-coded everything to save time, just to go over the high level. And then we're going to go through in the following videos, we're going to go in depth what each step is all about. So we load this up. We get our head for our data frame. See pregnancies, glucose, blood pressure, skin thickness, insulin, body mass index, pedigree function, age, and outcome. One thing that's sticking out to us is that there are 0 values here. We cannot work with 0 values because that's basically, in biometrics, this is null. You can't be 0, otherwise you don't have a live patient. And these people are certainly alive. So we're going to set these columns right here. We're going to set them to null. We're going to using this replace method, we're going to set them null. Then we're going to count up the nulls. Okay, we see we have quite a bit of null values in these columns. We're just going to drop them. So we've dropped a good bit of the data. And we're going to visualize using box plots So I've created a for loop here, going through the columns. With the exception of the outcome, I'm not interested in visualizing that. I do want to set a subplot. We box plot the given column with the title so we can identify it, and we just hit show. So we'll run that. And what do we have? Pregnancies, we got a few outliers. Glucose, blood pressure, we got outliers here and there. Skin thickness, we have one outlier. Body mass, no, this is insulin. Skin thickness, okay. Insulin, okay. It makes sense because we're looking at diabetic patients. They have trouble with insulin resistance, so they have elevated levels of insulin. Type 2, that is. Type 2 diabetes. Okay, looking at BMI. Okay, you got some outliers there. Diabetes pedigree function, we've got some outliers. And age, we've got a few. I guess most of them are very young, so the elder patients are outliers. Okay, what did I do here? We went right into transforming these values. All these outliers need to be transformed. It puts a control on the variance of the data, and we used a log1p transformation to get some control there. We're going to get into that. Okay, for column, then let's revisualize these. See what happened. So our variance was under control in one direction. So our blood pressure, now we have lower level outliers. Insulin. And we're just going to let these stand. I think in practice you might want to do more to work with these, but we're just going to let them stand for now. We're going to move on to step 4, which is to scale these features. So I'm going to import my necessary modules, all from sklearn, model selection, train test split. Preprocessing, we're going to bring in the standard scaler. Linear model, we're going to bring in logistic regression. And for metrics, we're going to bring in accuracy score, classification report, and confusion matrix. So let's split up our data here. From X, we're going to take out the target variable, and then we're going to put the target variable in Y. Then we're going to scale these data. X scaled, fit transform X. Now we're splitting. I've moved on to step 5. So train test split takes your data. Here we have X scaled and Y. So it takes your data inputs and your output, and it splits it up by whatever you set test size to. Here we split it up to 0.2. We want to set aside 20% of the rows, of the observations, to test our model. And then we set random state for reproducibility to 18. Here we train the model. So I'm setting to a variable model, logistic regression, model.fit. We're passing in xtrain and ytrain, which is 80% of the data set aside for this very purpose. We want to fit it to the model. And we're going to get into how this model works in the next videos. It uses a sigmoid function, which in turn uses a linear combination to fit the data into a decision surface of whether or not this patient has diabetes or not. So we train it here. We've done this, and it returns us back a little acknowledgement object here. Thank you. And now we evaluate the model. So this X test data that we've set aside here, we're gonna run it through the prediction, and then we're gonna measure that against the test outputs. So ypred, and how do we measure it? So I've made this. We compare ypred against ytest to see which ones are true, which ones are equal, which ones are not. And we sum those up and divide it by the length of the set. And so here I guess we get 79, which is less than what we've had before. 79 again. And we get a classification report. We can print a confusion matrix. And then we give it a new sample to make a prediction. So given these values, this model predicts that this patient has diabetes. So that's the life cycle of running through and applying a logistic regression model. Here we use the Indian Pima Diabetes set. So we collected our data. Well, thank you NIH for collecting that for us. We make sure that the values that were 0 were removed. We convert those to nulls, we remove them. We get an idea of where the outliers are. And because of these outliers, which we didn't really resolve properly, we didn't get the best score. I think 79 is probably not so great. But we import our sklearn modules, we split out the data, we scale it, we split it up again still into training and testing sets. We train the model, instantiate it, train it, throw in predictions, and then do some evaluation. Once again, we do more evaluation, and we make a prediction.